So let's get going here. So I just put up a little story just to illustrate really in the last slide that the techniques that we're learning about, which we're applying in this course to determine simple structures of simple organic compounds, apply to many different situations. And so this is just one from archaeology. Anybody in archaeology here? No? Geez. Make none of the students happy none of the time, right? But this is just some evidence that was accrued by using a combination of high-performance liquid chromatography to separate compounds and chemical ionization gas chromatography mass spectrometry. So this is the mass spec component here as a way to analyze the structure of those compounds. And by working that out, they were able to show that an extinct bison skeleton from 17,000 years ago had been poisoned by Mycobacterium tuberculosis, which is, of course, the cause of TB. So tuberculosis was around affecting a lot of people a very long time ago. And this just illustrates application of mass spectrometry. So let's start off by looking at the following problem. How could we distinguish this pair of structures, these pairs of structures? So the first one is an alcohol, and the second one is a ketone. So last week we learned how you could use infrared to tell whether you had an alcohol or a ketone, right? Alcohol, broad OH stretch, 3,300 centimeters to the -1 because of the OH bonds. The ketone has no OH bonds, so no stretch there. The ketone has a CO double bond, around about 1,700 centimeters to -1. Very strong absorption for all ketones. We learned about that last week. Whereas the alcohol on the left-hand side does not have a CO double bond. So infrared would distinguish those two compounds. Notice that the mass of the two compounds is the same. So mass spectrometry is going to tell us about molecular weights of compounds. In this case, mass spectrometry is not going to be a particularly good technique. And so this illustrates the key point that in solving chemical structures, we can never rely, almost never rely on one single technique. It's really the combination of a variety of techniques, including infrared and mass spectrometry, measuring the molecular weight of the molecule, that helps us solve the structure. In this case, infrared would be important. Mass spectrometry wouldn't really help us solve that problem. Look at the second pair. We now have two alcohols. Okay, the infrared spectrum of two almost similar alcohols really is going to be very similar. Both have OH stretches, and that's really all you can look at in the infrared. So the infrared spectrum is not going to help us in that second problem distinguish those two molecules. However, you'll notice that these two are no longer isomers. They don't have the same molecular formula, so they will have different molecular weights. And so if we can measure the molecular weight of the compound, and we can do that using mass spectrometry, then even if the IR doesn't help us solve the structure, then the mass spectrum will. Finally, I just very quickly introduce the third case. Okay, now we have two alcohols. Infrared spectrum won't distinguish them. These now are isomers of one another. Okay, have the same molecular formula, so their masses will be the same. In this case, neither infrared nor mass spectrometry will solve the problem. We need something else. And the something else we'll get to starting on Thursday, shouldn't say next week actually, and that is nuclear magnetic resonance. So this is like solving a crossword puzzle. Each spectrum, using a different technique, gives us part of the solution, but the whole solution only comes by looking at all of the spectra. So mass spectrometry primarily used to measure the molar mass and formula for a compound. So what we're going to do is vaporize the compound, get it into the gas phase. That will give us individual molecules. And then we're going to ionize the compound. We're going to convert it to an ion. So neutral molecule in the gas phase, still neutral. but we're going to turn it into an ion that can be a positive or a negatively charged ion. How are we going to do that? Well, the thing that has charges are electrons and protons. So we can make a neutral molecule charged by adding an electron to it. That will make it a negatively charged ion. By taking an electron away, that will make a positively charged ion, and that's the primary technique that we're going to focus on here. But both are used. And the final way that we could make something charged is to add a proton to it, and we'll look at that in electrospray ionization later on. So those are three ways that we can think of to get an organic molecule to take on a charge, a positive or a negative charge. In general, neutral molecules are stable. If I want to add an electron to a neutral molecule where all the bonding molecular orbitals are filled, where do I have to put an electron? All the bonding MOs are full. Got to put it in anti-bonding. So it's not going to be good. You're going to need energy to do this. If I want to add an electron to a neutral stable molecule, it has to go in an anti-bonding orbital, but the anti-bonding orbitals are there for electrons to occupy. If I put an electron into an anti-bonding orbital, it's going to make the molecule less stable. And we'll see in a little bit that this indeed happens and that bonds fragment when we make molecular ions, and that we also see some of those fragments in the mass spectrum. So the most common method of ionizing molecules, smaller molecules, this is probably not true anymore, but this is true for small neutral organic molecules. The most common method is electron impact. We put our sample into a mass spectrometer. Very high vacuum, lots of vacuum pumps. Molecule vaporizes. We have individual molecules in a vacuum. We then bombard with a beam of high energy electrons. In the old days, we used to talk about TV sets, right? You know, the old-fashioned TV sets that had big tubes in them that you saw your parents, grandparents lug about, right? Before there were nice flat screen TVs. And in those cathode ray tubes, there were beams of electrons. And the picture in the TV tube was created by a beam of electrons impinging, traveling very fast, impinging on the surface of the tube. It's exactly the same beam of high energy electrons, typically 70 electron volts for those physicists who care about putting numbers on things. And we hit a neutral molecule with a beam of electrons. These are very fast traveling electrons. They have lots of energy. They're way more energy than we need to fill an anti-bonding MO. In fact, these electrons have so much energy that they will knock another electron right out of the molecule. So we hit this molecule, for example, with a carbon-carbon bond in it, with a beam of electrons. That's a 2-electron bond. If I knock one electron out, I end up with a species that still is the same molecule, but now only has one electron holding the nuclei together. I knock an electron out, the impacting electron bounces off the molecule and goes away and knocks another guy out. If I lose an electron from a molecule, it's negatively charged, so the product that I get now has a positive charge. I've created a positive charge by taking an electron away from a neutral molecule. We refer to things that are positively charged as cations, but this also has an uneven number of electrons, and towards the end of this course we'll meet species with uneven numbers of electrons, non-filled orbitals, and so things with uneven number of electrons are called radicals. This is called, therefore, a radical cation, and this is the species that we make by ionizing the molecule. The mass of the radical cation is essentially the same as the mass of the molecule. I've knocked an electron out, but electrons have very little mass, right? 1/1800th of the mass of a hydrogen atom. So that when I do this, the radical cation still has the same mass, to all intents and purposes, as the neutral that I started with. If the radical cation remains intact, it's commonly known as the molecular ion or the parent ion of the compound that I have ionized. Sometimes the molecular ion undergoes fragmentation. That's because we now have a very weak carbon-carbon bond here. Two nuclei held together now only by one electron, not the pair of electrons that we had in a stable bonding arrangement, but a single electron holding the nuclei together. And of course, this now means that I have a much weaker chemical bond there. So it's then easy for this bond to break. If the bond breaks, then I end up with a radical that's neutral at one end and a cation at the other. So fragmentation results in a radical that is not charged, 7 electrons, 1 electron short of the octet, and a carbocation that is positively charged. So we then take these ions that we've created by bombarding our molecule. Now the ions are accelerated through an electric and magnetic field. The ions are deflected by a magnetic field. Used to the idea that charged things interact with a magnetic field. And so these ions are created by electron impact, accelerated towards a negatively charged plate, and then they pass through a magnetic field where they will be bent over to one side and arrive at a detector right here, right? Positively charged ions go one way, negatively charged ions go over here. So they're deflected in the magnetic field, and the amount by which an ion is deflected in the magnetic field depends on the charge. For our purposes in mass spectrometry, the charge on these ions is always going to be +1. Okay, so the charge is constant, but the amount by which a charged species is deflected in a magnetic field depends not only on the charge, but also on the mass. So we take a bunch of molecules, we turn them into radical cations, pass them through a magnetic field, and they are sorted according to mass. So a mass spectrum is the result, it's a measure of the number of ions arriving at the detector as a function of mass. Technically, here's a mass spectrum. So technically, the x-axis is mass to charge ratio, because that's the amount by which an ion is deflected. But if z, the charge, stays constant at +1, we're really measuring mass, right? So x-axis is mass, or mass to charge. Here is the mass spectrum of methane, CH4. Remember, we've seen that methane has the carbon atoms sp3 hybridized. Mix the atomic orbitals, overlap, blah, 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 sp3, tetrahedral, etc., right? So I take a molecule of methane, vaporize it in the mass spectrometer, no problem vaporizing this because methane's a gas to begin with. Blast it with electrons, knock one electron out of one of the CH bonding molecular orbitals. That gives me CH4 dot plus, the molecular ion or parent ion. The CH4 dot plus passes through the magnetic field. It's sorted according to its mass to charge ratio. Carbon is 12, hydrogen's 1, so methane should be 16. So I should see ions arriving at the detector with mass to charge 16, and indeed they do. You can see that there's a peak there at 16. So x-axis is mass to charge. The y-axis here is usually called relative abundance. Let's just call it the number of ions with that particular mass to charge ratio. Okay? So we're getting a lot of ions arriving at the detector at mass to charge 16, corresponding to the mass of methane. Let's turn all that into reverse. We take an unknown compound, we put it in the mass spectrometer, we blast it with electrons, make radical cations. Radical cations, we sort the radical cations according to mass to charge ratio. And so then for our unknown compound, all we really have to do is read the mass spectrum and we get the molecular weight of the compound. Right? Problem solved, if you will. Except that as we saw in the previous slide, it's actually a bit more complicated than that, but this will give us a very useful piece of information that will help us determine structure. So here is the mass spectrum of methane. If I took an unknown compound, looked at this mass spectrum, I would say that this compound has a molecular weight of 16. Obviously, I'm reading the peak furthest to the right, the one with highest mass. And you'll notice that there are other masses. There's actually a little bit of 17, and we'll talk about where that comes from. And there's quite a bit of 15 and 14 and 13 and even 12. These are fragment ions. These are ions that are created, they're still charged, but they're created by CH4 dot plus, the initial radical cation, the parent ion, fragmenting, losing 1, 2, and 3 hydrogens. So in this case, the base peak is the tallest peak in the spectrum. In this case, the base peak is M to Z 16. It's the most intense, the largest number of ions arriving at the detector have mass to charge 16, telling us this is methane. But there are other peaks, fragment peaks, that result from breaking up of the radical cation, and that gives rise to 15, 14, 13, and so on. In fact, with electron impact, sometimes if the molecule really wants to fragment and fall apart, sometimes we don't even observe the molecular ion peak. And in those cases, we might then have to switch to different softer ionization techniques that give us radical cations more readily in a less excited state, less prone to fall apart. Okay, so how do we get 15? 15 illustrates fragmentation. Molecular ion, CH4 dot plus, one of those CH bonds has only one electron holding the nuclei together. If that bond falls apart, I can produce H dot, that's the hydrogen atom. It's neutral, not separated in the magnetic field, but I also get CH3 plus, methyl cation, that is charged, it weighs 15. So it will get sorted in the mass spectrometer and give rise to a peak of 15. Yeah. At 17, and we will get to 17. Yes. Okay? So we're working our way through. We explained 16, that's easy. That's our molecular ion. 15 illustrates fragmentation, and we fall apart to make methyl plus. We can even lose further hydrogen radicals. We can fragment even more to make 12, 13, and 14. 12 is just a carbon atom, right? It's lost all its hydrogens and has a positive charge. So the M plus 1 peak, the peak at 17, is the result of isotopes. In this case, 1% of the molecules of methane have a carbon-13 atom, naturally occurring isotope of carbon, carbon-13. Carbon-13 weighs 13. 13 plus 4 hydrogens is 17, so the 17 ion comes from that. So in reading a mass spectrum, we have to be a little bit careful, but we can get the molecular weight. What is the molecular weight of a compound? It's basically looking for the peak of highest mass to charge ratio. Things with lower mass to charge ratio must be fragments of bigger things, right? Little things can't fragment into big things. Doesn't make sense. So if we wanted to determine the molecular weight of this sample, we would recognize that 12, 13, 14, 15 must be fragments, breakdown fragments, of a bigger piece, and that is in fact 16. So we look for the peak furthest to the right. It's not always the most intense peak. We're looking for the peak of highest mass. That tells us the molecular weight of the compound, with the exception that we have to be aware that there will be little things at higher weight because of isotopes. Okay. Mass spec is a relatively sensitive analytical method. So organic compounds that are identified by mass spec, we can get away with tiny amounts of material. We're counting ions arriving at the detector one molecule at a time. Infrared, we need quite a chunk of sample, as you'll see in the lab. But with mass spec, we can detect femtomoles of materials. And so this makes mass spec very sensitive. We can analyze very small amounts of things like pharmaceuticals, drug discovery, drug metabolism, right? One of the things that you have to do if you're a pharmaceutical company is you have to prove what happens to, you want to sell a new drug, you have to prove what happens to it in the human body. You have to prove how it metabolizes. And so that is a tricky problem. We're going to have small amounts of drug, large amounts of blood that contain small amounts of drug, and mass spec, being sensitive, is a way to essentially measure those tiny little needles in a haystack in a mixture. Amino acid sequencing in biotechnology, analysis of macromolecules, this can be done by mass spec. Clinical analysis, many clinical analyses use techniques in combination with mass spectrometry, neonatal screening for inherited genetic diseases, many of those screens, hemoglobin analysis, looking for defective hemoglobin, all those sort of clinical processes involve mass spectrometry to analyze the, for the molecules. Environmental forensic explosives detection, rather apropos these days. So when you go to the airport and they take a little swipe thing inside your suitcase, right? I guess most people have been through that, right? They take a little cloth and they wipe it and they stick it in a big sort of square boxy machine. That is actually a mass spectrometer that is looking for compounds with the molecular weight and fragmentation pattern that are predicted for known explosives. Okay, many, many more applications. Here's benzene. In this case, we have a more complicated mass spectrum, a lot of ions. Okay, and here now we can read off the molecular weight of benzene easily. All these little things here are fragments. Because benzene's a ring, fragmentation is less prone to happen. In order to fragment a ring, you have to break two bonds, right, to make smaller bits. If you only break one bond in a ring, you still have the same molecular weight. So less fragmentation in benzene. Here now we can read the molecular weight at 78 here. We move along, we look for the peak at highest mass to charge ratio. That's the thing that is most likely non-fragmented, bearing in mind that we may have another little peak just a bit further up due to heavy isotopes of things like carbon-13. Okay, here's pentane. In the case of pentane, we don't have a ring. Fragmentation is easy. So now here's a mass spectrum, more typical mass spectrum. How do we determine the molecular weight of pentane from this spectrum? We do not look for what's called the base peak, the peak of highest intensity, because that peak is not the peak of highest molecular weight. So it's two different things here. The peak of highest molecular weight that tells us the molecular weight of the compound. Here it's 72 for pentane, okay? So we get information from that peak. The peak that has the highest relative abundance, the most common ion in pentane, is the fragment ion shown here. So the first step in analyzing mass spec is to identify the M dot plus peak, tell you the molar mass of the compound, and from that we can get some information. Odd-massed molecules may well contain 1, 3, or any odd number of nitrogen atoms. Most organic compounds actually have an even molecular weight. Combine 12 for carbon, 1 for hydrogen, even number of hydrogens. Oxygen is 16, nitrogen is 14. So when we do all those combinations, we find that most molecules that lack nitrogen have even molecular weights. So if we find an odd molecular weight ion, that is an indicator that nitrogen atoms may be present in the molecule. Even massed may indicate an even zero or an even number of nitrogen atoms. Okay, so the M plus 1 peak here, the peak at 17, results from the presence of C13 in the sample. We mentioned that already. Carbon-13 is the heavy isotope of carbon. Normal, 99% of all carbon atoms in your body in this room are carbon-12, right? But 1% of all of our carbon atoms approximately
is actually a heavy isotope weighing 13. It's only a tiny amount, but mass spectrometry is separating molecules one molecule at a time. We are not looking, as we did in infrared, at the collection of all the molecules in the sample. We are counting them, dividing them by molecular weight, one molecule at a time. So any given molecule of methane, 99% of the time the carbon will be a carbon-12 and it will weigh 16. But 1% of those molecules, that carbon is a carbon-13. It weighs 13, and a methane molecule therefore weighs 17. It is separated as an individual molecule in the mass spectrometer, and so it comes out at a different mass to charge ratio. So here is decane. 10 carbons now. The molecular weight of decane, C10H22, is 142. So we see a good strong molecular ion for decane. The M+1 peak is now quite big. It's almost 10%. Even though the abundance of carbon-13 is only 1%. Why has it grown so much? In decane, there are 10 carbon atoms. What are the odds of all of them being carbon-12? It's 0.99 to the power of 10. Right? That actually goes down significantly. What are the odds of one molecule having carbon-13 in it? At any given site, it's 1%. But there are 10 different sites. So it's like flipping a coin, right? What are the odds of flipping a head 10 times in a row? Very slim, right? The odds of one of those being a tail are actually built up, right? So the odds of a decane molecule having one carbon-13 in it is approximately 10 times the odds of carbon-13 of any particular atom being carbon-13. In other words, 10 times 1%, so we see about a 10% signal in decane. This is actually kind of useful. If we measure the ratio of M to M+1, we have a way to determine the number of carbon atoms in the molecule. So not only do we have the molecular mass of decane, but we can also tell by looking at that signal intensity for the M+1 peak, in fact, that there are 10, or at least approximately 10 carbon atoms in the molecule. So we don't just get a mass, we actually get a count on the number of carbon atoms. In fact, many molecules have isotopes. Fluorine is one. Here's a question. How do I tell? I've got an alkyl halide. How do I tell whether it's a chloride or a bromide? Okay? The bond stretching frequency in the infrared, that's way down in the fingerprint region, not reliable. So mass spectrometry, of course, will tell me immediately whether I have an alkyl chloride or a bromide, because chlorine and bromine have totally different molecular weights. But actually, it turns out that we have another way to tell whether a molecule contains chlorine or bromine, or how many halogens it contains. And that is the fact that if you go to the periodic table and you look up the molecular weight of fluorine, you want to calculate 1 mole of NaCl, it's 35.5, right? But there are no individual atoms weighing 35.5 in there. That is the average for billions of atoms. And we get to 35.5 because chlorine, individual chlorine atoms are sometimes chlorine-35 isotope and sometimes chlorine-37 isotope. They differ by 2 mass units. Chlorine-36 is unstable, radioactive, not part of the equation. So molecules with chlorine often have a very characteristic distribution of mass to charge peaks. Here's chlorobenzene. Okay? Lots of fragment ions, but if we look at the molecular ion, there's a mass peak at 112. That's the molecules that contain chlorine-35, 3/4 of all chlorine. And then a smaller peak, not at 113, but actually at 114. 2 mass units away. So this sort of pattern, 3 times the intensity to 1, differing by 2 mass units, is strongly indicative of a molecule that contains chlorine.
So we get the molecular weight of this compound by looking
at the molecular ion, peak furthest to the peak of highest mass to charge ratio. In this case, it's 112 for 35 chlorine and 114. That presence of that extra M+2 peak,
strongly indicative of the presence of chlorine in the molecule. Bromine gives us a different pattern.
Bromine, we go to the periodic table and you look up the molecular weight of bromine to measure a mole of sodium bromide, it's 80. But there are actually no atoms of bromine 80 in there. Bromine 80 is unstable, it's radioactive. You get 80 by averaging billions of molecules, half of which are 79 bromine and half of which are 81 bromine. There are 2 stable isotopes, 50-50 crapshoot, that a molecule will contain a 79 or an 81. But in mass spectrometry, we're separating molecules 1 molecule at a time. So as a molecule passes through the mass spectrometer, it's got to be either a 79 or an 81. It's only got 2 choices. Right? Half the molecules arrive at the detector at mass to charge 150, whatever here, and then the other half of the molecules 2 mass units higher because they're the molecules that contain bromine 81. So the key thing that you really need to understand about mass spectrometry is that it tells us the molecular mass of the compound. 90% of everything that you do in this course will be along the lines of an unknown compound gave a molecular ion in the mass spectrometer at mass to charge 157. The infrared spectrum showed peaks at 3,100 centimeters to the minus 1. Okay, and later the NMR spectrum showed deducer structure for the product. Okay, so 90% of what you need to know you already know from this lecture, and that is that mass spectrometry gives us the molecular weight. But in fact, we're learning a bit more detailed stuff here. You don't have to memorize all this shit, right? About the details here.
The key point is that mass spectrometry gives us the molecular weight,
but what we want you to recognize is that in fact the information content is a lot higher. You can tell how many carbons there are in that molecular ion. You can tell whether it's got chlorine in it, whether it's got bromine in it,
and so on and so forth. Okay, if we go back to the pentane spectrum, okay, then we find
that pentane can fragment at any one of the carbon-carbon bonds. So we see a whole bunch of fragment ions. If I fragment the first bond, I can make the butyl cation and a methyl radical. I can fragment the second bond to make the propyl cation, ethyl radical, ethyl cation, methyl cation. Those radicals aren't charged. They don't get separated and detected in the mass spectrometer because they have no charge. Mass spectrometry measures mass to charge. But the cation fragments are charged. They will accelerate in the mass spectrometer towards a negatively charged plate, make a beam, separate the beam by mass to charge. So we see the fragment ions only, not the fragment radicals, but the fragment ions.
So here is the spectrum of pentane again.
We saw that. There's M dot plus at 72. That's our molecular ion. Not the biggest peak in the spectrum, but the peak furthest to the right-hand side, with the exception that at 73 there is the predicted isotopomer containing carbon-13. You'll notice here that the fragmentation pattern now is logical. M minus 15, that's loss of a methyl radical to make a butyl cation. M minus 29, that's loss of 2 carbons to make a propyl radical. Fragmentation of 3 carbons makes an ethyl radical, and we see that peak at M minus 43. And M minus 57 is actually formation of CH3+,
the methyl cation.
Notice that the intensity pattern here is different. The best fragmentation, the most common fragmentation, the one that gives you the highest relative abundance is actually fragmentation down the middle to make the propyl cation and the ethyl radical. We haven't seen this yet, but along the way in this course you'll learn that positively charged carbons, carbocations like CH3+, CH3+ is less stable than ethyl or propyl or so on. Okay? That actually more alkyl groups in a carbocation gives you more stability, and we'll come back to that point as we look at the SN1 reaction in chapter 7. But effectively that is causing this distribution, uneven distribution of fragment ions. What can we get from fragment ions? And in ye olde days of yore, before good techniques like NMR were invented, when mass spec was the state of the art for determining structure, there were people who were very good at looking at fragmentation patterns and working out how you could learn from the fragmentation pattern how to put the structure together. Is that easy to do? Looks like a bitch. Really, really tough to do. Okay? Not easy by any stretch of the imagination to look at a spectrum like that and say, oh, it's pentane, linear pentane, and not 2-methylbutane. Right? Both have the same molecular weight, but they have different fragmentation patterns. So you are not expected to learn a lot about fragmentation in this course. The main purpose, as I say, is that mass spectrometry, gives you the molecular weight of the compound, but there is a lot more information in a spectrum. Okay, tertiary carbocations, as we'll see, are very stable. So in this particular case, this is 2,2-dimethylpentane. In this case, very hard to see the molecular ion because we have a molecule that can fragment to very stable fragments in this case, and breaking that bond to make a carbocation, a species with 3 separate alkyl groups attached, a so-called tertiary carbocation, is particularly favorable. There are many other fragmentations, and all possible fragmentations are observed to some extent, and this is because in electron impact we're blasting the molecule with a beam of very high energy. Okay, I'm going to skip over several slides here. I left these in place just because they are in the textbook. If you are very good at mass spectrometry, and you will not get this good almost certainly, right, you will recognize that there are certain patterns of fragmentation. Alcohol molecular ions break particularly easily along the carbon-carbon bond and give rise to ions that are resonance stabilized, and on Thursday we'll talk about resonance in chapter 2. So, particular fragmentation patterns are common. Amines, carbonyls undergo the Clafferty rearrangement. So, many of these things are named after famous pioneers of organic chemistry who worked out the hard way that you could work out molecular structure by understanding fragmentation. We're not going to do that, and we're going to move on. So fragment ions are important in determining structure. High-resolution mass spectrometry, this is just a way of saying that we can measure the molecular weight of our ion, not just to plus or minus 1 mass unit, but in fact, in a sophisticated mass spectrometer, we can measure it to 4 or 5 places after the decimal point. So, protons and neutrons have different masses. So, in fact, various different isotopes, proton, deuterium, carbon-12, carbon-13, okay, have slightly off-integer absolute masses. So relative atomic mass of carbon-13 is not 13.0000, it's 13.0034. It's not exactly 13, okay? So each of these different isotopes of each of these different atoms has a different exact mass. You won't need to use these or memorize these exact masses for the course. And in fact, you won't be given a table of them because you don't have time in a test to sit down and add up 15.000999 and 14.777, right? You're not going to get a molecular formula that way. But this is simply to point out that here are two compounds with molecular weight 84. One is cyclopentanone, it's a ketone. One is cyclohexane, a molecule that we'll talk about a lot later in the course as we look at structure. Both have formal molecular weights of 84. But they have different formulas, C5H8O, C6H12, different molecular formulas. So if we use those exact masses, then we find that the two different formulae, two different structures, are actually have different exact masses, right? One is 84.0573, one is 84.09 something, so they're different. So if we have an unknown compound with molecular weight 84 and we measure the mass very accurately, we can in fact get an accurate high-resolution mass that will allow us not just to determine the molecular weight of the compound, but actually to have a pretty good guess at the molecular formula. So, so we can do that. Mass spec is suited, regular mass spec is suited to identification of pure substance. If I put a mixture of two compounds into the mass spectrum, it's going to be very difficult to determine if I have two separate molecular ions or I have one ion and its fragment, right? Because of fragmentation, we don't just get a single signal from a single compound. So this means that mass spectra of mixtures are very complicated, hard to interpret. But we can do some cool stuff, and we can take a chromatograph like a GC that separates molecules by chromatography. Okay, so we have a typical gas chromatograph with a column that's separating compounds by their polarity. We then take the eluate from the GC, we can feed that in to the mass spectrometer. So this is gas chromatography coupled to mass spectrometry. This is cool because you separate the compounds in the GC, you separate them based on time, and then you get a bunch of peaks coming off the GC. By coupling it to a mass spectrometer, you can determine the molecular weight of the compound that comprises each of those individual peaks. Okay? And so this is a technique that's used a lot for complex mixtures. We separate the mixture first, get a bunch of peaks coming off the column, and then look at the mass spectrum of each of the individual peaks to determine their molecular weight. So there's a typical chromatogram, detector signal versus time. The mass spectrum, low-res or even high-res mass spectrum, to give us the molecular formula, can be measured for each of those techniques. Gas chromatography is a great technique for detecting small molecular weight volatile compounds. They need to be delivered in the gas phase. In gas chromatography, we separate things by using a gas as the mobile phase, passing over a liquid as the stationary phase. So our molecules need to be volatile. They need to at least be partially in the gas phase. So how do we tackle large biomolecules? Okay, and we have to recognize that GCMS isn't going to work. To be analyzed by electron impact mass spectrometry, the technique that we looked at in detail earlier on, substances must be vaporized prior to ionization by the electron beam. So we can't do that. Compounds that decomposed before they were vaporized could not be analyzed by mass spectrometry in the old days. But in fact, the desire to analyze large biomolecules by mass spectrometry has created better ionization techniques. In electrospray ionization, we can take a liquid sample, for example, a protein or a nucleic acid. We spray the liquid into the vacuum of the mass spectrometer through an electrospray needle that creates charged ions, and so we can in fact get very large biomolecules like proteins into the gas phase with a charge on the molecule, and that allows us to separate those proteins by mass. So we can work out molecular weights of proteins in the tens of thousands of Daltons. ESI is a softer technique, which also is useful because soft ionization techniques don't leave excess energy in the molecule to cause fragmentation. And so with very large biomolecules, fragmentation would be an issue if we used hard ionization techniques. You can couple HPLC columns, high-performance liquid chromatography. So this is liquid chromatography, liquids passing over a solid stationary phase. And so you could then couple an ESI, electrospray ionization mass spectrometer, to the outlet of an HPLC. So this allows you to separate molecules that are really non-volatile on a chromatography column in the liquid phase, and then analyze their molecular weight as the peaks come out in the mass spectrometer. So the electrospray ionization, so LCMS, liquid chromatography mass spectrometry. So one of the things that you can do is then say, in a very complex sample, like a blood sample that you're testing for doping, you know what you're looking for. You're looking for the doping agent, right? If you're the, I don't know, the people who check for doping, what are they called? International Olympic Doping Committee, whatever, dope heads, I don't know, whatever, those guys. All right, so if you're one of those, what we can do is we can take a very complex sample like blood containing thousands of compounds, put it and separate those out by HPLC, analyze with a mass spectrometer, and then ask the question, are any of the peaks that are eluting from the gas chromatograph, do any of them have the molecular weight that we expect for the doping agent? So that allows you to cut away all of the molecules that you're not interested in with different molecular weights and detect essentially the needle in the haystack. That, in this case, would be the doping agent at the molecular weight that you know that it occurs at and at the retention time that you expect to see. So mass spectrometry has evolved a lot. There are a lot of sophisticated techniques, but each of them in the end is really telling us mostly about the molecular weight of the compound. Something that we can get once we have a formula for an organic compound is to work out the degrees of unsaturation. So compounds that lack any double bonds follow the general formula CnH2n plus 2. So alkanes, propane, butane, pentane, all follow the formula CnH2n plus 2, where n is an integer. And so we call these saturated. There are no double bonds, no degrees of unsaturation. If, on the other hand, we have an alkene, that's 1 degree of unsaturation. Notice that the formula for pentene is not CnH2n plus 2, it's CnH2n. So by working out the carbon to hydrogen ratio, we can determine the number of double bonds that are present in the molecule. So here's a compound with 2 degrees of unsaturation. We can have 2 double bonds. Okay, so consider the isomers of C4H6. Okay, there's 2 degrees of unsaturation here. It's not CnH2n plus 2, it's not CnH2n, it's C4H8 minus 2, CnH2n minus 2, 2 degrees of unsaturation, 2 double bonds, so there are 2 isomers with 2 double bonds, a couple of compounds with 1 triple bond, but rings also count as a degree of unsaturation. So even once we have the molecular formula C4H6 in this case that we've determined by mass spectrometry, okay, we still have not solved the structure problem. Mass spec has helped us solving structure problems. It's told us about the molecular weight of the compound. Infrared has helped us solve structure problems because it's told us a certain amount about functional groups. But even the combination of mass spec and infrared would still not be enough to sort out this problem. Which of these 7 or 8 structures here that we actually have.
There are some rules for degrees of unsaturation that I'm going to read with you.
Halogens count like hydrogens.
Oxygens don't count.
Different students approach this different ways, right? So you can work out the hydrogen deficiency index, which is the same as degrees of unsaturation, following the formula 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus halogens, add all that up and divide by 2. And that formula works. It will give you correctly the number of degrees of unsaturation. And some of you are quite happy with formulae. How many people like to learn a formula like that? They're all sitting at the back. Telling somehow that. Okay, so here's another way to do it, right? I want to know what the formula is for an alkane. Now something with no degrees of unsaturation. I draw ethane, C2H6, CnH2n plus 2. So, you know, you can start from all the regular alkanes and work out what it would look like if there were no double bonds and no rings. And then work out what you've actually got. And if you have 1 degree of unsaturation, you have 1 double bond or a ring, 2 degrees of unsaturation, various different combinations. So, calculating the hydrogen deficiency index can be useful. Okay, so if you find a molecule with 0 hydrogen deficiency index and you want to solve the structure, you cannot draw a structure with rings or double bonds.
So there's a little exercise for you. Propose a structure with a molecule formula
C7H12O that has these absorptions
in the infrared, and you will find that actually there are
several solutions to this. So even knowing the molecular formula and knowing the infrared, we still need more to determine the structure of the molecule.